Alright, so good morning everyone. Hope everyone's having a good day so far. Today we're moving on to Chapter 4, Section 8, Analyzing Graphs of Polynomial Functions. Once again, this is kind of a long section, so we're going to kind of break it up into two parts. We are almost done with Chapter 4. Thank goodness, this has been a really long chapter, but we are almost through with it. So let's get into analyzing graphs of polynomial functions. So in this chapter so far, you have learned that zeros, factors, solutions, and x-intercepts are all closely related concepts, topics. So here's a little summary of those relationships. So let f of x equal a sub n x to the nth power. You guys can read all of that yourself. Just let that be a polynomial function. The following statements are equivalent if that is a polynomial function. K is a zero of the polynomial function f. X minus k is a factor of the polynomial f of x. K is a solution or root of the polynomial equation f of x equals 0. And then if k is a real number, then k is an x-intercept of the graph of the polynomial function f. The graph of f passes through k, 0. So we've learned about that all throughout this chapter. If I have a solution to my polynomial function, it crosses the x-axis, it's an x-intercept. So let's look at an example real quick. Using x-intercepts to graph a polynomial function. It says graph the function f of x equals 1/6 times x plus 3 times x minus 2 squared. So the first thing I want to do is identify my x-intercepts, my zeros. So remember, if it's already in factored form, I can just set each factor equal to 0 and solve for x. So subtract 3, I get x equals -3. Add 2, I get x equals 2. So I can go ahead and plot these points on my x-axis. So I'm going to go left 3 on my x-axis and put a point. Go right 2 on my x-axis and put a point. Those are my zeros, aka my x-intercepts. So there's my x-intercepts. Now I want to get more points that are on my curve. So that way it can help me draw my curve a little more accurately. So what I'm going to do is pick some x values that are around -3 and +2. So I'm going to use -4, -2, -1, 0, 1, and 3. I'm going to plug those x values into my polynomial function to get some more points that are on my curve. So we said -4, -2, -1, 0, 1, and 3. I'm just going to plug all those in to my function, and that'll spit out my y value, my f of x value. So I'm going to plug -4 in. So f of -4 so -4 plus 3 would give me -1. -4 minus 2 would give me -6. -6 squared is +36. -1 times 36 would be -36. And then 1/6 times -36 would give me -6. So one of my ordered pairs is -4, -6. So I can go left 4, down 6, and put one of my points. So there's another one of my ordered pairs that's on my graph. Now I need to plug in -2. -2 plus 3 is 1. -2 minus 2 is -4. Negative 4 squared is positive 16. 1 times 16 is 16. And then 1/6 times 16 would give me 16 over 6, which reduced down would give me 8/3. So I get negative 2, comma, 8/3 for another one of my ordered pairs. 8/3, if I get that in decimal form, that would be about 2.67. So I'm going to go left 2, up 2.67. So that'd be somewhere in this area right here. So there's another one of my ordered pairs. Plugging in negative 1. Negative 1 plus 3 is 2. Negative 1 minus 2 is negative 3. Negative 3 squared is 9. 2 times 9 is 18. 1/6 times 18 is 3. So I get negative 1, 3. Left 1, up 3. If I plug in 0, 0 plus 3 is 3. 0 minus 2 is negative 2. Negative 2 squared is 4. 3 times 4 is 12. 1/6 times 12 is 2. So I get 0, 2. I'm going to go through these last two a little quicker. F of 1. 1 plus 3 is 4. 1 minus 2 is negative 1. Negative 1 squared is 1. 4 times 1 is 4. 1/6 times 4 is 4/6, which reduces down to 2/3. So 1, 2/3 would be about there. And then lastly, plugging in positive 3. Three plus 3 is 6. 3 minus 2 is 1. 1 squared is 1. 1 times 6 is 6. 1/6 times 6 gives me positive 1. So 3, 1. So now I've got a bunch more ordered pairs graphed that are actually on the graph of my polynomial function. So now another thing that's going to help me is knowing the end behavior of my polynomial function. So remember, with end behavior, we want to know if our leading coefficient is positive or negative, and we want to know if our degree of our polynomial is even or odd. So if I were to multiply all of this out, I'd probably start off with x minus 2 times x minus 2, because it's x minus 2 squared. That would give me a quadratic. The degree of that polynomial would be 2. If I multiply that x plus 3 into that one, my degree of that polynomial function would be 3. It'd be a cubic function. And then if I multiplied my 1/6 through all that, my leading coefficient would be 1/6. So that would mean my leading coefficient is positive, my degree is odd. So if you remember from your end behavior chart that I told you guys to put in your notes, back in 4.3 or 4, I can't remember, it was one of those sections, we know that f of x goes to negative infinity as x goes to negative infinity, f of x goes to positive infinity as x goes to positive infinity. So it's going up and to the right, down and to the left. So now I know my end behavior. So now that I have all my points that I want, and I know the end behavior of my function, I'm going to go ahead and draw the graph so it passes through the plotted points and has the appropriate end behavior. So I know it's going down and to the left. It's coming up and curving through all my points. And it's going up and to the right. So there would be the graph of my polynomial function. Hopefully that wasn't too terrible. It seems like a long process, but once you kind of get going on it, it gets a little quicker. If you have questions on it, please make sure you're letting me know. Let's move on to the next topic. The next concept this is called the location principle. So it says you can use the location principle to help you find real zeros of polynomial functions. So here's my actual location principle. If f is a polynomial function and a and b are two real numbers such that f of a is less than 0, aka if I plug in a, I would get a negative number, and f of b is greater than 0, so if I plug in b, I get a positive number, then f has at least one real zero between a and b. To use this principle to locate real zeros of a polynomial function, find a value a, here's their a value in this example, at which the polynomial function is negative, and another value b, at which the function is positive. You can conclude that the function has at least one real zero between a and b. So let's think about this real quick. If I have a value that I plug in and I get a negative number, and I have a value that I plug in and I get a positive number, those are both going to be on the graph of my polynomial function. So if I'm connecting those points, it's going to have to cross the x-axis somewhere to connect a point that's negative and a point that's positive. So I know I'm going to have at least one real zero because it's going to cross my x-axis. So let's look at an example. It says find all real zeros of f of x equals 6x cubed plus 5x squared minus 17x minus 6. So the first thing I'm going to do is I'm going to start plugging x values in to see if I can get a negative value and a positive value to pop out in my y value column. So I have an x column and an f of x. Remember, we treat f of x just like y. So I'm just going to start with the number 0. If I plug in 0, the first term is going to give me a 0. Second term is going to give me a 0. Third term is going to give me a 0. And then I have minus 6. So if I plug 0 in, I get negative 6. So there's a negative value. Now let's plug 1 in. Let's just go down the list. F of 1. So I get 6 times 1 cubed plus 5 times 1 squared minus 17 times 1 minus 6. 1 cubed is 1. 1 times 6 is 6. 1 squared is 1. 1 times 5 is 5. Negative 17 times 1 is negative 17. And I still have that minus 6. 6 plus 5 is 11. 11 minus 17 is negative 6. Negative 6 minus 6 is negative 12. I have another negative. That's okay. I can just keep plugging values in. Remember, I want a negative and a positive value. So let's try the number 2, f of 2. So 6 times 2 cubed plus 5 times 2 squared minus 17 times 2 minus 6. 2 cubed is 8. 2 squared is 4. Negative 17 times 2 is negative 34. 6 times 8 is 48. 5 times 4 is 20, minus 34 minus 6. 48 plus 20 is 68. 68 minus 34 is 34. Not negative, it's positive 34. And 34 minus 6 would give me positive 28. Looky there. We got a positive value. So I know that somewhere between 1 and 2, I have a real root of my polynomial function. So let's use our rational root theorem real quick to list out our possible rational roots of our polynomial function. So I'm going to list out factors of my constant term, 6, plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6. And let's list out factors of our leading coefficient. Plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 6. Now I need to put all these factors over all of these factors. Plus or minus 1 over 1, 2 over 1, 3 over 1, 6 over 1. Now I need to put them all over 2. I already have 2 over 2 because that can reduce down to 1 over 1. I already have 6 over 2 because that reduces down to 3 over 1. Excuse me. Now I need to put them all over 3. I already have 3 over 3. I already have 6 over 3. And now I'll put them all over 6. I already have 2/6. I already have 3/6. I already have 6/6. So here's my list of possible rational roots. Now remember, based on my location principle, I want a root that is between A and B. So in this case, I want a root that's between 1 and 2. So I'm going to go eliminate all the ones that are not between 1 and 2. 1 is not between 1 and 2. 2 is not. 3 is not. 6 is not. 1/2 is not. Positive 3/2 would be 1.5. So that would be between 1 and 2. Let's see if there's any others. 1/3, 2/3 is not. 1/6 is not. None of the others are between 1 and 2. So it's looking pretty promising that 3/2 is going to be my real root. Hopefully you guys remember how to check it. We're going to use synthetic division to check to see if positive 3/2 is a root of my polynomial function. So I have 6, 5, negative 17, negative 6. Bring my 6 down. 3/2 times 6 is 9. 5 plus 9 is 14. 3/2 times 14 would give me 21. Negative 17 plus 21 would give me 4. 3/2 times 4 would give me positive 6. Negative 6 plus 6 is 0. Since I got a remainder of 0, I know that 3/2 is a factor, or a 0, of my polynomial function. So let's factor it out real quick. If it's positive 3/2, it's going to be x minus 3/2. And then we use these as our coefficients for our polynomial function in this set of parentheses. So I get 6x squared plus 14x plus 4. So now I need to see if I can factor this polynomial any further, because I'm trying to find all the zeros of this polynomial function. So I do have a GCF in this polynomial. The GCF would be 2, so I can factor out a 2. 2 times 3x squared would give me 6x squared. 2 times 7x would give me 14x. 2 times 2 would give me 4. Once again, like in the past, I can distribute this 2 through this set of parentheses, so I don't forget about it. So that'd be 2x minus 3. Now let's see if we can factor this polynomial any further. I might have to use some slide and divide here. So I'm going to multiply that 3 times that 2. So that'd give me x squared plus 7x plus 6. Let me see if I can factor this. I'll list the factors of 6. I know my two signs are going to be plus and plus. So 1 times 6 gives me 6, and 2 times 3. Adding across, 1 plus 6 gives me 7. 2 plus 3 gives me 5. I want the one that adds to give me 7, so I know it's positive 1 and positive 6. Don't forget to divide by the thing we multiplied by earlier. So I have to divide both things by 3. Reduce your fractions. 1/3 is already reduced. 6 divided by 3 gives me 2. If you have any fractions left, remember bottoms up, the denominator comes in front of the x. So 3x plus 1, and then I have my x plus 2. So I can go ahead and bring this part over here. So we have f of x equals 2x minus 3. And then we have 3x plus 1. And then we have x plus 2. So I have now factored my polynomial. This guy right here, I've factored it completely. So now I have to actually answer the question. I need to actually find the zeros of this polynomial function. So I just set all my factors equal to 0 and solve for x. So add 3, divide by 2. We already knew that x equaled 3/2. Using our location principle and our rational root theorem in synthetic division. Subtract 1, divide by 3, x equals negative 1/3. Subtract 2, x equals negative 2. So my three zeros of this polynomial function are 3/2, negative 1/3, and negative 2. So I answered my question. I found all my zeros. Hopefully that location principle makes sense. Once again, you want to make sure, you want to see if you have a positive value and a negative value when you plug some numbers in. And based on the location principle, you know you have a real zero between those two values because it would have to cross the x-axis somewhere. So that's all the notes I have for you guys today. We'll finish the notes up tomorrow on the second part of 4.8. Today's assignment is page 224, numbers 3 through 21 odds. This will be due, I think we have an assignment due on Monday, so let's make this assignment due on Tuesday, the 23rd of February on Canvas. If you have any questions, please make sure you're letting me know. Hope you guys have a good rest of your day, and we'll see you next time.